Building an AI agent today usually means wiring together a sprawling mess of file types. You have prompts and text files, tool schemas in JSON, and callback chains in YAML. Because the agent's logic is fractured across all these different layers, tracing a single decision, let alone testing or version controlling the agent, becomes a massive orchestration headache. NVIDIA Labs just released a framework designed to fix this. It is an Apache 2.0 open-source research preview called NVIDIA Object-Oriented Agents, or NEWA. NEWA abandons the fractured architecture entirely. Instead, it collapses the entire agent into a single native Python object. By treating the agent as standard software rather than a disjointed graph of API calls, developers can return to normal testing, standard Python profiling, and refactoring workflows. The current agent harness has become a development bottleneck. NEWA attempts to clear it by completely rethinking the underlying architecture of an agent. In early testing, this architecture allowed NOAA to score 82.2% on the SWE-bench Verified test for real-world GitHub issue resolution. More importantly, it achieved that score using roughly half the token consumption of comparable open-source frameworks. To understand this drop in inference costs, we have to look closely at NOAA's pass-by-reference architecture. But that efficiency comes with a severe trade-off. NOAA uses a code-as-action model that requires the LLM to write raw Python, a design that compromises standard framework-level containment. We are going to build the NOAA object to see exactly how it cuts token spend, and then detail why deploying it requires strict OS-level isolation. Adopting NOAA forces a direct choice between reasoning efficiency and out-of-the-box deployment safety. This diagram shows how the framework maps traditional concepts into Python. We start by defining a single class that inherits from NOAA's base agent. Instead of hiding critical data dynamically inside a chat history array, state lives explicitly in the class fields. A standard Python method inside this class runs exactly as written. This keeps fixed business rules, like checking refund eligibility, entirely separate from the LLM. If a method's body contains only an ellipsis, the framework hands that specific function over to the LLM runtime to solve. There are no separate JSON tool schemas. Standard Python type annotations dictate the required output. If the model returns the wrong shape, the framework automatically rejects it and forces a retry. The instructions for the model don't live in a separate prompt file. The Python docstring sitting directly under the method name serves as the explicit prompt for that specific loop. By embedding prompts and tool contracts directly into the object syntax, the developer and the LLM now share the exact same interface. This split-screen diagram illustrates the token bloat problem. Traditional frameworks must serialize massive database objects into giant JSON strings just to feed them into the LLM's context window. NOAA uses a pass-by-reference design. The full database remains intact in Python memory. Only a small reference tag travels into the context window, keeping the token count low. Instead of reading the entire object as a string up front, the LLM receives a bounded preview, interacting with live data through helper methods as needed. The quantitative impact of this architecture is highly visible on the SWE-bench Verified test. NVIDIA reports NOAA completed tasks using approximately 1.1 million tokens, while comparison open-source harnesses required roughly 2.2 million tokens to achieve similar reasoning results. Preventing large inputs from being serialized into the prompt structurally halves inference costs on complex data tasks. We have to look at how the LLM actually uses those reference tags, because it creates a serious security reality. NOAA operates a code-as-action paradigm. The LLM writes and executes raw Python code in a real-time loop to interact with those live objects. This diagram illustrates the resulting security paradox. Writing live Python inside the host process gives the model high-level reasoning capabilities, but it also grants access to arbitrary files and libraries. NOAA includes an abstract syntax tree validator and module deny lists, but NVIDIA explicitly states these are just defense-in-depth measures against common errors. A static code check is not a true containment boundary. It cannot stop malicious or hallucinated code from escaping into the host system. Because of this, NOAA must be run inside strict OS-level isolation. Whether it is a Docker container, a virtual machine, or NVIDIA OpenShell, the boundary must be absolute. NOAA's high performance demands infrastructure-level security, precisely because the framework is designed to give the model dangerous in-process access. Beyond the core object, NOAA features an optional extensibility module called the Memory Manager. This package handles asynchronous consolidation outside the active agent loop. It merges duplicates, links concepts, and prunes decayed data without slowing down immediate tasks. This transforms simple chat logs into a typed, queried knowledge graph. The model can actively reflect on this structured data before taking a turn. On the ARC-AGI-3 benchmark, applying this memory system over standard file-based notes improved NOAA's performance score by nearly 12 points. Explicitly managed, database-backed memory substantially outperforms passive chat history logs for complex, multi-step reasoning. NOAA is worth a 30-day technical pilot for teams heavily invested in Python who are building agents that must manipulate large, live data objects. But those adopting teams must have the DevOps maturity to build and maintain their own OS-level sandboxes and least privilege credentials. Teams requiring highly durable execution, strict human-in-the-loop workflow checkpoints, or managed SLAs should avoid NOAA for now. Existing orchestration runtimes like LangGraph remain better suited for enterprise-grade state machine resilience. Keep in mind that NOOA is currently a 0.x research preview, meaning its public API is subject to breaking changes between releases. NVIDIA has shown that turning an agent back into a single native Python class can substantially cut token costs and simplify testing, provided you can secure the execution environment. As foundation models achieve parity, the agent harness, how it handles state, safety, and tokens, is rapidly becoming the primary differentiator in AI engineering.